Hi everybody, welcome to week 4 of the course. Last week we looked at classical trade theory, the Ricardian model, looking at comparative advantage versus absolute advantage. This week we're moving to a new trade theory, a new trade model by firstly looking at chapter 4, chapter 5, chapter 6 and chapter 7. It is important to know that chapter 4, 5, and 6 are the building blocks needed for the HO model, the Heckscher-Bochelen model that we will be covering. So let's get started looking at the HO model. So the main component which this model is based on is looking at differences in relative factor endowments. And based on those differences, it will determine how international trade actually flows. The previous model that we did, the Ricardian model, looked at technology differences and determined trade flows were based on differences in technology. So who actually contributed to the HO model? So in our case, we might call it the HO model or the HOS model, it's up to you. But all the letters in the naming of the model belongs to someone who has contributed towards the model. So the main contributors were Ali Heckscher, Bertel Oechlen, and Paul Samuelson. And what we're going to be concentrating on is looking at two factors of production or two inputs. Those factors of production are going to be labor and capital. And we're going to keep in the idea that for our production function, we're going to have constant returns to scale. And we'll discuss a bit about that a bit later. We also have optimizing economic agents, and they're going to be optimizing based on taking consideration perfect competition, and we will also be given prices. So prices in the market are given already. It's not determined in this model. And as I said before, what we looked at last week in chapter 3 was the idea of technology differences. In this case, for our model, there is no technology differences. Both countries that we will be dealing with, or all countries that we will be dealing with, have identical technology. So it's trying to show, okay, trade is determined in a different way. So what are our assumptions? So we're dealing with two countries, right? That's what we're going to limit our model to. Two countries, we can assume Australia and Bolivia in this case. We have two final goods, food and manufacturers. In our case, we're going to assume that food is labor intensive. So it uses more of the labor input. And we're going to have manufacturers, and we're going to assume that that is capital intensive. So we're meaning that that will use more capital relative to labor. We also have the two factors of production, which we just mentioned earlier, which is capital and labor. And we have constant returns to scale production functions. What does that mean? If I double my inputs, I expect my output to also double. So it's like for like relationship in a sense. That's going to help you to determine the optimal solution where we need to land up with. It also makes the math a bit more easier. Dealing with perfect competition, so that is for our agency to take in consideration and for our firms to take in consideration how to derive at an optimal solution. We're always going to assume that a firm is what? Profit maximizing, and we'll get there a bit later. We're also assuming capital and labor is mobile, but mobile only within a country, but not between countries. So it won't move from Bolivia to Australia or from Australia to Bolivia. There's no labor movement there. There's no capital movement there. But within Australia, where they have two sectors, they have the food sector and the manufacturing sector, labor and food can move between those sectors. Remember, what is the main difference that we are already seeing here between the Ricardian model? Ricardian model and the HO model's main difference in terms of factors of production is that labor was only considered for the Ricardian model. For the HO model, now we see Capital is also included. Remember, those stuff come in terms of MCQ questions. Sometimes they come in terms of discussion that discuss the main differences between all the models that we do for the year. Then. So then you need to understand what are the bases and assumptions that these models are based on. We also have costless trade in final goods. That differs in a sense that both the Ricardian model and the HO model both have this costless trade in final goods assumption. While the gravity model does discuss the idea that there are certain things that impede trade, and they do mention it. Is it factored in the model? In terms of the formula, no. The formula of a gravity model only considers distance and the size of the countries, right? The size of the country's GDP. Anyways, we're also dealing with identical production technology between the two countries or in the two countries that we mentioned earlier. So no trade will occur because of technology differences. They are exactly the same in terms of their technology makeup. Meaning, what does that mean? Think about it. And then we also have no factor intensity reversal. So we're not going to have the idea that food which is labor intensive will become capital intensive in that. We're not dealing with that type of idea for what we're discussing for chapter 4 and chapter 5. And then we're also dealing with identical and homothetic tastes in two countries. What does homothetic taste means? Or identical or homothetic in a sense means that you can take demand or the consumer side and then represent it in terms of a utility function. And there's a special property that you can assign to this utility function, which in a way says that if you increase your consumption of the two goods, food and manufactures, say you double your consumption in food and manufactures, that would mean that your utility would double too. So it's homogeneous of degree 1. And you can go read up an idea of what homogeneous means and degree 1 and then. That would be a nice interesting thing you would do. If you have not done it in ECO335, you would at some stage have done it in microeconomics. If not, you will definitely for certain see it in honest economics, honest microeconomics. And then the last thing and what determines or is the basis for the HOS model is the idea that they differ in terms of their factor endowments or their relative factor endowments. So a country like Austria might be very abundant in capital, and someone like Bolivia might be very abundant in terms of labor. Then you would maybe say Bolivia is a labor intensive country and Australia is a capital intensive country. Maybe that would mean then that Bolivia would probably produce more food relative to manufactures, and Australia and Austria might be able to produce more manufactures than food. Sorry if I use Australia and Austria interchangeably, but I meant Austria throughout the slide. So there are 4 main results of the neoclassical model, 4 propositions that we need to discuss. I'm not going to do the word for word explanation. You can go and read what is on the slides, go and read your book and maybe do a deeper explanation. I'm going to try to put this in layman terms or use examples to make them easier. So let's look at the first proposition, the factor price equalization. So this is the idea that, and I'm going to do it in terms of the two countries that we are discussing. So here we have Bolivia and we have Austria. They're going to interact with each other and trade. Once they trade, at the end, the wages in Bolivia and the wages in Austria will be exactly the same. It's the same for the price of capital inside Bolivia and the price of capital inside Austria. So the factor prices become the same over time. So how much you're going to pay for renting capital is going to be the same regardless of which country that you're actually going to. That's the first idea. But there must be trading that occurs between the two countries. The second idea is the Stolper-Samuelson theory, And that's just the idea that when the price of a final good increases, then the rewards for the factor production that is used intensely in that production will increase. But on the other hand, the reward for the other factor production would decrease. What am I saying here? I'm saying the idea that say manufacturer price goes increases, manufacturing price is increasing, so manufacturing goods price is increasing. What good is used intensely, or what factor of production is used intensely there? That is a capital intensive production. So the rewards for capital would increase, but the rewards for labor would decrease. The third theory, the Rybczynski theorem, deals with the quantity of a good, or the quantity of a factor of production. So it says when the quantity of that factor of production increases, then automatically we would use or increase the production of the final good that uses that factor of production intensively. And on the other hand, the other good would suffer. So in our case, let's assume we have Austria. All of a sudden, there's more capital available in the country magically or something. So now the quantity of capital has increased. They would then produce what more? They will produce manufacturing goods more, because manufacturing goods are more capital intensive. Right. At the same time now, they will produce less, or they will decrease their production less of food, which is more labor intensive. And then lastly, the main part, our theorem that we need to get to, the Heckscher-Oberlin theorem, that's got to do with labor intensities or the quantity of labor inside a country. So this basically says that you will export the good or the final good that uses or makes relative use or intensive use of the relatively abundant factor of production. What does that mean? That means that if, for instance, Austria is a capital intensive or capital abundant country, it will produce what? It will export the good that is capital intensive. So capital abundance leads to capital intensive, which leads to the export of that capital intensive good. So in the case of Austria, they are capital abundant. They therefore they would then have or export the capital intensive good of manufacturers. So this is something you need to take in consideration. And Bolivia, being a labor abundant country, would export the labor intensive good of food. Okay, let's look at some of the neoclassical production functions. So there are a couple we need to look at. The first one is not any surprise. We have capital and labor as inputs. We have the idea of substitutability. That means I can swap out labor for capital and vice versa. So given any output that I'm trying to produce, I can use either a lot of capital with a little labor, or a lot of labor with a little capital, or equal amounts in a sense. But they can be exchanged for each other, but not like for like or one-to-one relationship. It can be different. So what I mean by that is, if I decide I wanted to use one less of capital and replace it with labor, so by reducing my capital by one does not necessarily mean I only need one labor. I might need more than one labor or less than labor to keep that same level of output. I'm also dealing with positive marginal product, meaning that if more capital or labor is used, then output would be increasing still, right? There's nothing about, okay, I'm going to use more labor or more capital, and oh no, the amount of output decreases. In the real world, that can exist, right? You can find that I hire one more guy inside a firm, and this guy, he just causes negativity. He somehow affects everybody's marginal productivity, or he just cause a ruckus in that, or he sabotages business, then it can occur, right? There's other more technical ways of looking at it, and we're not going to look at that in that sense. We also have the idea of diminishing marginal product. So if I hold capital constant, I'm not changing capital, I'm keeping it fixed. By me using more and more labor, the amount that I'm gaining in terms of output, it's going to still increase, but at a decreasing rate. Understand what that means? So capital is not changing. I'm adding one more unit of labor. When I add that 1 unit of labor, it might give me maybe 10 more products are being produced. Then I add another one labor. Now instead of me getting 10 more of that product increase, I might now get 9.9. And similarly, when I add another labor, instead of getting 10 more of the product increasing, maybe get 9.6. So we have this idea of diminishing. It is increasing the output, but at a decreasing rate. And then we're also dealing with constant returns to scale. This is nothing new. I've explained this before. Any increase or increase in the use of both inputs by 10% would lead to an increase in output by 10%. Simple as that. So what does the production function look like? We're going to restrict our work to the manufacturing industry and not the food industry. The same analysis will occur in the food industry. So here we have M to denote manufacturers with the quantity on the manufactured products. K here will represent capital, L will be labor. Both of these are inputs in the production. So these are the amount or the number of capital and labor used. And then we have alpha M, which is the capital intensity parameter. The larger that value, the more capital intensive the production is. And then finally, right at the bottom, we have the production function, which is just the manufacturing. The number or the product of manufacturers is equal to the product of capital and labor. Remember, capital and labor are both affected by this capital intensity parameter. You should also note that if you add alpha and 1 minus alpha, we will get 1. Why is that 1? What type of production function are we dealing with? Constant returns to scale. So any constant returns to scale function, both exponents will add to 1 in the production function. There are other ways to show it, but for now, this is just all that you need to know. So isoquants and production functions are linked to each other. Isoquants are when you fix the quantity in a production function. So you might say that M, the amount of manufacturers, is equal to 1, and then you look at the various capital and labor that you need, or the quantities of labor or capital that you need in order to produce that one quantity. So what we already done is defined M, we defined capital, we defined labor, and we defined alpha. And remember that alpha is between 0 and 1, right? For our cases. And that is your production function that appears. That is not new, that was done on the previous slide. But the actual drawing of the production function is a convex line. So it's a curved convex line. Why is it curved and why is it convex? The curving and the convexity of the thing is representing what? The diminishing marginal returns, right? So it's curved and convex because of diminishing marginal returns. But the line itself is showing the various capital and labor that is needed to produce this fixed quantity, or in other words, to depict the isoquant. So if you look at the far left of the graph or the line towards the top, a high amount of capital and a low amount of labor is needed to produce this fixed quantity. Towards the center of the curve, it's more or less similar amounts of labor and capital is used. Not exactly the same, but close enough values in terms of labor and capital. And to the far right of the line, will have a high amount of labor and a low amount of capital that is needed to produce this fixed quantity. So all these combinations of capital labor that you do have for this fixed quantity, this is what we refer to the isoquant. So let's look at a production function in terms of constant returns to scale. So what do we know? If we increase or decrease the inputs by a certain proportion, right? Both of them, labor and capital by a certain proportion, then we expect output to decrease by the exact same proportion. So in our case here, we have an isoquant where we've chosen the quantity to be equal to 1. The quantity of manufacturing goes equal to 1. We also have a point A1 that is represented on this line. We're going to also do later, we find another point on this line. We can assume that the inputs of A1 are reduced by 30%. So what does that mean if the inputs are reduced by 30%? The output value is also going to be reduced at 30%, meaning M now at this A2 will be 0.7. Similarly, if we did the same thing for B, reducing the inputs at B by 30%, we're going to find that M is equal to 0.7. So we can now draw a new isoquant between B2 and A2. And that will represent all the values of all the capital and labor quantities that will give us an output of 0.7. A new isoquant basically that is equal to 0.7. You could have done this, you could have added more points, a C1, a C2, and shown all the shift backwards of 30% and then joined all the values to have a more accurate depiction than that. But that is the main thing you need to pick up, that the isoquant will shift under reduction to the left and under increase in inputs to the right, because it's representing the quantity, a fixed quantity for the production function. So profit maximization is a two-step procedure, and we're going to link this to our production function. So firstly, profits is revenue minus production cost. That shouldn't be anything new. And what are our two steps now of maximizing profits? The first idea is to say, okay, let's say we want to produce a certain amount. What is the minimal cost that I can incur for this amount of production? So what is the least amount of capital costs and the least amount of labor costs that I would incur to produce a certain amount? And then secondly, we're going to determine the optimal output level. So let's now move to the cost minimization step, right? This was the first procedure or the first step of the profit maximization. So I have an isoquant, M equal to 1 there given. So this is where we're limiting output equal to 1, right? Now we're going to try to find what is the most ideal cost or the lowest cost that we can incur to produce this amount of quantity. So we need to assume there's a wage rate. So we're going to call this wages or the wage rate W. And then we're going to call, and that is going to be a link to our labor, right? How much you pay for labor. Then we're going to have also something associated with capital, and this is called the rental rate, which is R. And that will give us our cost function, right? Our total cost function. We need to know the cost of labor. The cost of labor is W times L. The wages we pay someone times the amount of labor we use. Similarly, the cost of capital will be RK. The rental rate times the amount of capital we use, and that will give us a total cost function. Then we need to find the slope of that function, of the total cost function. The slope of the total cost function is negative W over R. How are you going to find that? You take your total cost function and write it in terms of capital. Capital needs to be made the subject of the formula. Why? Because capital is your Y What is capital? It's your y variable, right? It's on your y-axis. So whenever you needed to do your parabolas or your straight lines back in the graph, what they were in terms of? They were always in terms of your y variable. Y equals mx plus c. So now we're making our y variable in this case, which is k, the y variable. So we're going to write k as the subject of formula. So we're going to have km equals to everything else, right? So you need to write that total cost formula in terms of km. And that will show you the slope of the cost function is negative W over R. You will see that value W over R in front of the labor variable once you rewrite that equation, right? It's a nice exercise. Go try that at home. So now you land up with the slope function. So we have this line, this red line, negative WR, which represents a total cost function. Any total cost function, right? This is not any specific value, right? Where this line originally starts is not cost minimizing, because we can use on that line a high amount of capital and labor to produce that quantity, but we can actually use a less amount. So the lesser amount, or the base value of our total cost, would then rather occur at the point of tangency, when our cost function is tangent to our isoquant. So that means we need to take this line and shift it downwards. Right? We have to shift it downwards up till the point of A. And that is going to give us our cost minimization point. And that will also then, because we shifted this graph or this line downwards up till the point of tangency, that will determine the amount of capital and labor that we need to employ or hire to produce the output of 1. So what in terms of constant returns to scaling production costs have we actually done? So by using constant returns to scale, we find that the isoquants are just radial blowups of each other. What does that mean? That kind of means, in a sense, that because we use m is equal to 1 as our isoquant, when we try to do the mathematics and graphical analysis of using m is equal to 2, all we have to do is take all our values and scale it up by how much production has increased by. Is that interesting? You don't need to repeat the mathematics and all the technical calculations that you've done for m is equal to 1. We didn't do any other mathematics in this graphical analysis. That will be part of your tutorial. But all you have to take into consideration, that same mathematics I did under that scenario, when I change to a newer isoquant, I don't need to repeat the mathematics. All I have to find out is, okay, what is happening in my production function? It is double. And now because it's double, what does that mean in terms of my revenue? What does it mean in terms of the amount of labor I'm going to use? What does it mean in terms of my capital to use? Everything just gets scaled up. No need for calculation. You scale it up by that factor that has affected the isoquants, and that's it. So in terms of minimizing production costs, which is now simpler to calculate, all you have to do is say, okay, if that 1 unit of output doubled, then my capital would double and my labor would double. All right, that's why we kept our m equals to 1. Because when m is equal to 1, when we do anything to output, it's easier to calculate what the increase is, upwards and downwards. Right? If you move from 1 to 3, what is that? Well, how much increase is that? Right? What percentage is that? If you move to 1 to 2, what is the percentage increase for that? It's 100% increase, right? Or doubling. So if you're doubling, it makes then the calculation in terms of capital and labor easier, right? So this is what I'm basically saying, right? This is the second step, right? When you increase your output by Z units, then proportionally the units of output that of inputs that you use to produce the Z amount of output is also going to increase by that same amount, right? 100% increase in output, 100% increase in terms of capital, 100% increase in terms of labor. Hence the word radial blowups. just inflating stuff upwards and downwards in the same proportion. And then when you try to work out your total cost, all you need to do is say, okay, what is per unit cost? I just need to time that by our output. Nothing too special. So now we need to bring in the idea of perfect competition. So now what do we establish? We established earlier profits was, what was profits? The total revenue minus your cost, right? In our case, that can be simplified in terms of the price minus the per unit cost altogether times by output. Right? What is price times output? That is your revenue. What is your per unit cost times output? That is your cost. And that gives us three scenarios. If you're selling your product less than what it actually costs you to produce the product, are you at some optimal level or not? No, you're not. Right? This is not where you want to be. You're making absolutely no profit. So you're not going to find yourself producing at all. You don't want to interact in a position where you are producing, but the cost is far outweighing what you can actually sell the product for. What happens when your price is equal to unit cost? In terms of perfect competition, when your price is equal to unit cost, what is that? That is actually perfect competition. Then you're actually at your optimal level. But how much profit are you making? Zero. Right? Exactly what you're selling your product for, exactly what it's costing you. And that is what perfect competition is. There is no profits under perfect competition. But there might be accounting profit, right? When I'm talking about profits, I'm talking about economic profit. And then the third scenario, you can find that price is more than your unit cost. What do you do in that case? How much are you going to produce in that case? I will produce an infinite amount. If I'm getting always a profit on every unit I'm producing, because the price I'm getting back is more than what it's cost me to produce, I'm just going to keep producing, because I'm getting profit back all the time for everything I'm selling. What does that mean in terms of my profit? If I'm getting profit back for every unit that I am producing, and I'm producing infinite amount of units, then I'm getting infinite amount of profit. But does that exist in an economic equilibrium? Unfortunately, no. Why? We're dealing with perfect competition, right? So in economic equilibrium, unfortunately, that would never exist. That is ideal situation, right? If you can produce an infinite amount and make infinite amount of profit in it. So unfortunately, with constant returns to scale and perfect competition, what that would imply that at least the prices must be less or equal to our unit cost. And we were producing at least more than zero output. But that only occurs when the prices is equal to the unit cost. So what you should be taking from this, everything is a graphical analysis, right? Some of the mathematics will be tested with the tutorials where you need to actually go and read the work. Some of this should be very familiar because you would have done this in ECO335. But just now there's a lot more letters than actual numbers in that. But you shouldn't be unfamiliar because the prerequisite or for moving to a third year economics now is that you would have done micro, macro, econometrics, and the mathematics course. On the other side, let's move to what happens if wages fall, if the wage rate fall. So the initial point we are at A, we're assuming the initial wages was W0, that was the slope of the line, and we had M equal to 1. Nothing special, isoquant M equal to 1. So this is the point that we're depicting in terms of our cost minimization point for point A, right? So what happens when wages fall? What does that mean, the cost, in terms of the cost of labor? The cost of labor is falling, right? But what does that mean in terms of your slope? If W is becoming smaller, what does that mean? My slope of my line is becoming more horizontal or more flatter. Alright, so we've just drawn that in. That's your green line. That is a depiction of what your new slope of the line. We need to now cost minimize with this less steeper line or flatter line to a new point B. So that means we're going to shift the line downwards until the point of tangency, which occurs at point B. Because wages has fell, we have a flatter line or more horizontal line, and that will give us the point B, right? So remember what we're trying to do. We're still trying to produce one output, right? We're not changing the amount of quantity or moving to a new isoquant because it's a change in wages. We're still trying to keep our output fixed. We just want to find what is the new optimal point on our isoquant that where we need to produce at in terms of the labor capital when wages changes. Remember, the same analysis can be done in terms of a wage increase, a rental of capital increase, and a rental of capital decrease. Just remember this, right? So, okay. So now once the slope has become flatter, we find ourselves at B. What is B? B relative to A, what has happened? Because wages have gotten cheaper now, we find ourselves that we're actually using more labor. And we're using less capital. So the amount of labor has increased while the amount of capital has decreased because wages has become cheaper. So you can assume then if wages had gone up, what would have occurred? Lastly, for chapter 4, we're going to compare food to manufacturers. Food has a lower capital intensity than manufacturing goods. We're going to keep W and R the same. So wages and rental income is going to remain the same, which also means that the slope of the lines is going to be the same for the manufacturing industry and the food industry, because both of them, their total cost function slopes are the same. So when we depict the food line or the food isoquant, it is the green line. It also has a lower capital intensity, meaning its alpha value associated with it is less than that for the manufacturers, which has a higher alpha value. Finding the point of section, that just means finding the point of intersection or the point of tangency. That is just shifting the red line upwards until it is tangent to the green line, which happens at point B. What we can see is the capital at point B, the amount of capital, the number of capital at point B is far less than what is at capital than the capital of A. And the labor at point B is far more than the labor at point A. What does this mean? It means that the capital ratio at B, capital to labor ratio, is lower than the capital to labor ratio of A. So for production structure, chapter 5, some concluding remarks. We find that the HO model explains trade flows based on differences in relative factor abundance. There were also 4 main propositions that we covered. We also know there were 2 inputs that we used, and they're both under constant returns to scale. And we also looked at cost minimization input combination. Depends on what the alpha value we choose, the capital intensity, that was just the slide before this, and it depends on the wage rental ratio. Right? When wages changes, this affects the inputs, so and so and so. These are very, very important for when we eventually actually do the HO trade model. And we also know with constant returns to scale and perfect competition that a good is produced where price is equal to the production cost per unit cost. Finally, moving to chapter 5, an overview of what we're going to look at. We saw with the HO model that it focuses on factor abundance and capital intensity. Henceforth, we will assume manufacturers are relatively capital intensive. As you've seen with my discussion, you will probably see that I have already assumed that. We also see that food is also relatively labor intensive. Or equivalently, the alpha value of food is less than the alpha value of manufacturers. So in this chapter, we're going to use the learner diagram. And what are we going to look at? We're going to look at the factor price equalization, which we discussed earlier as a theorem. But that's the idea that factor prices are the same between countries under trade. And then we will also look at using that learner diagram for the Stoppler-Samuelson theory. And that's the idea that if a price of a final good increases, the reward to that factor used intensely in the production of that good and increases, and the reward to the good, the other factor of reduction, decreases. So we need to establish what the unit value isoquant is in order for us to refer to in the learner diagrams. So by definition, a unit value isoquant. This is not an isoquant, it's called a unit value isoquant. It's the output needed to produce 1 unit of value. So we're valuing the quantity, right? But it must equal to 1. So if price is equal to 1, and the isoquant value or the quantity value is of m is equal to 1, then we have a unit isoquant. Because 1 times 1 is 1, right? That's what we're want to land up with. You want to know, have prices times m to be equal to 1. So what happens if we change prices to 2/3? If we change prices to 2/3 and we want a unit isoquant, a unit value isoquant, then we need to make m 1.5 because 2/3 times 1.5 is going to equal to 1. So if we see this, an isoquant of unit value means prices times the m value has to be equal to 1. So what we can see then that is the unit value isoquant depends inversely on price. When prices go down, then the quantity would go up, or the value for m would go up, and the other way around too. So now we need to define the unit value isocost line. So that is the input combinations leading to one unit value of cost. Meaning when we take wages times by labor and we add to that the rental value of capital times by capital, then we should get 1. At the same time, we can draw this. We can do this by finding the x-intercept and the y-intercept, or in our case, the labor intercept and the capital intercept. When you're finding the labor intercept, you must make capital 0, and then you solve for labor. And when you do that, you will find that is equal to 1 over W, as you see on the x-axis. At the same time, when you find the capital intercept, or the y-intercept in this case, you have to make labor equal to 0. Solving that then finds that capital is equal to 1 over R0. So what happens when the cost of capital or the rental value of capital goes up from R0 to R1? That shifts the graph to the left. Right? Remember we established the intercept is 1 over R0. Now it's going to be 1 over R1. And R1 is a larger value than what R0 is. So 1 over R1, 1 divided by a larger number is far larger than 1 divided by a number that's slightly smaller than that. Hence why the graph actually shifts inwards to the left. It's important to remember this, right? When for a unit value isocost line, when the rental rate goes up, the line shifts inwards to the left. That's different when we deal with isocost lines earlier. Right? It's a bit of a different discussion in terms of slope, right? But now we are restricting the graph to equal to 1, and that's why it's causing slightly different changes, but correct changes, because it's relative to what assumptions and restrictions that we have placed for the work that we're covering. So now we're going to derive the learner diagram. We can have the unit value isoquant curve for the manufacturing industry and for the food industry. We're going to assume that prices for manufacturers is equal to 1. That forces the unit value of the isoquant or the manufacturing indices quantity to equal to 1 as given. Then we're going to assume that the food indices price is equal to half, and that will force the quantity value or the isoquant value, the unit isoquant value of food to equal to 2. Remember, half times 2 is going to be equal to 1. We need to keep that value steady at 1. So we also now need to recall that under constant returns to scale and under perfect competition, there's absolutely zero profit that exists, right? We're at the place where prices is equal to the per unit cost. So that also implies that when we draw in this curve, right, where all the values are equal to 1, where the unit ISO quant value is equal to 1, or the manufacturing and food industry, and the unit value of the ISO cost curves is equal to 1, we're going to find that when we draw in the ISO cost line and we're going to make a tangent, we will find that it is tangent to both curves, to both the isoquant of food and the isoquant of manufacturers. That will leave us at point A and point B. That is important. That is why we're keeping the value at 1 so that we can actually find that the unit value of the ISO cost line is tangent to both the unit value isoquant of manufacturing and the unit value isoquant of food. And this here is called the learner curve. So these assumptions that we made was to derive this learner curve or the learner diagram. So the learner diagram is going to allow us to show that when given the final good prices, we can actually determine the factor prices. And when given the factor prices, we can actually find the final good prices. So in a sense, it's a one-to-one correspondence between final goods and factor prices. And then we can also look at the corollary of which is called the factor price equation, which I'm not going to go through again, right? So we can look at all those ideas. Okay, so let's assume you're given the final good prices and we want to determine the factor prices. We're only doing this by diagrams, right? So you're given the final good prices P and PF. What do you know? That the unit value of the isoquant for manufacturers will be 1 over PM, because 1 over PM times PM must equal to 1. Similarly, given the final good price of PF for foods, we know that the unit value isoquant value is going to be 1 over PF. And then we can draw that. What do we also know? We also know the point of tangency that is going to occur can only be in one place. So that's why we draw in this tangent line that goes through A and B. So you're given the isoquants, and now you know, wait, we're working with unit value isoquants and a unit value isocost lines which are equal to 1. That forces the graph to be only tangent at point A and B. Once you determine A and B, you can actually then work out what the wages and the rental rate is. So it's like working backwards, because you know everything has to equal to 1. You get the prices, you find the isoquants, the unit isoquants. Once you find the unit isoquants, you know that the isocost line is also equal to 1. It will be tangent on both graphs, and only at one point you draw that in. Once you draw in that isocost, unit isocost line in, that will then determine your wages and your rental rate of capital, right? Or the cost of capital. So let's do the reverse. Let's say you get given the factor prices. So get given the factor prices. So you know what W and R is, and you know that the unit isocost line can be drawn in, right? So that's going to be the red line that we depict. Right? We know that W times L plus R times K must equal to 1. And we know there's only one tangency point that can occur with manufacturers. So we find that point relative to the isoquant, the unit isoquant, And we know at the same time there's only one tangent point with the isoquant of food, and then we capture that. This is only graphically, right? Once you determine that, it allows you to find what the isoquant value is. Once you define the isoquant value for manufacturers and food, you can actually then find the prices for both those final goods. So the inverses are quite nice. And you can obviously expect that there is obviously a depiction beyond graphs. There is actually can be mathematical and a calculation for this. And I don't think you will be getting any mathematics. If you do, it might be in the form of tutorial just to explore. But in terms of testing in an exam, it's very unlikely that you will be getting chapter 5's work in terms of mathematics. But there is a good possibility that you might get the mathematics of chapter 4. Even though I didn't go through it, the mathematics, and I stick to the graph form, expect that you will get tested so you can actually go read through that chapter and work through the math in form of a tutorial. So finally, we can look at the Stolper-Samuelson theorem using the learner diagram. So what we're going to look at in the next few slides, we're going to look at manufacturing product or the manufacturing good. We're going to look at what happens when that product's price increases. And we know that manufacturing product is capital intensive. We're going to look at how the rental rate or the reward to capital rises and the wage rate falls. Similarly, but we're not going to show this, and this might be an exercise for your tutorial if it's not actually in your lecture slides. Then we're going to look at the idea that if the price of food rises, then the wage rate rises and the rental rate falls. So that is not actually shown here in class, right? And together, both this analysis is the Stolper-Samuelson theorem. So here we are with the learner diagram, and we're looking at the Stolper-Samuelson theorem. We have manufacturers, which is a relatively capital intensive good, and we have food, which is a relative labor intensive good. So now we're going to assume the price of manufacturers increases, and when that increases, the isoquant has to shift inwards to ensure that the value cost remains 1. Right? This is something we did earlier, right? With the inverse relationship. When prices go up, the isoquant value goes down. The M value goes down. This is what we have. We have a shift leftwards or inwards of the isoquant in order to ensure that the value of the isoquant remains equal to 1. So now we need to find the point of equilibrium. We have a new isoquant line, which is the dotted blue line, and we still have the old green line for the manufacturing industry. Remember, our equilibrium point is where the unit isocost line is tangent to both the manufacturing industry and the food industry. So we need to find a point or an isocost line that is tangent to both the dotted blue line and the green line. So we can draw that in, and that is going to give us the point A prime and B prime. Those are our two new points of equilibrium. But what had to occur to bring about that equilibrium? What happened in terms of the factor prices? If we look in terms of the rental rate of capital, that increased, or the reward towards capital increased. Right? We find ourselves at the new point, 1 divided by R prime. Right? It's as simple as saying, okay, if 1 over R is decreasing, then that means R must be increasing. At the same time, we also find that 1 over W is increasing, which means that wages is decreasing. So this is what the Stolper-Samuelson theory is showing. And you can show the same depiction in terms of the food industry, where maybe the food price increases and you have to do again the same analysis. But remember, for equilibrium, it needs to be tangent to both the new isoquant line that is occurring and that of the other industry. And finally, to summarize the remarks of chapter 5, we looked at the one-to-one correspondence between factor prices and final goods that existed. We found the idea of equalization of factor prices when we are trading final goods, and we also found a rise in the price of a final good leads to an increase in the reward of the factor used relatively intensely in its production, and obviously a fall in the reward of the other factor. That was just the slide before this.